Okay, so at the end of the last video, we had been talking about our different types of waves, transverse, longitudinal, and surface, which is based on the way the wave is making the particles move. So in transverse, the particles are vibrating up and down, but the wave is traveling perpendicular to it. And the easiest way to see this one is to think of what you do when you're at a wave at a sports game. Right? You stand up, sit down, but the wave travels around the stadium. You don't get up and run around with it. Longitudinal, the particles are vibrating back and forth in parallel to the direction the wave is moving. This really would be our vocal cords, right? So my vocal cords push up this way and it pushes the molecules together. So you get an area where the molecules are together, and then when my vocal cords vibrate backward, the molecules spread out, and then up again, they're together, and then they spread out, okay? So, but they're vibrating in the same direction as moving. And then the surface wave would be like water, where if you watch, or if you've ever been floating in the ocean, you know that you bob up, over, down, back, and you move around in a little circle, sometimes perpendicular, sometimes parallel with the motion. All right, so now today we need to take a look at some different terms. So the wave I drew was really the one that you'd be used to, the transverse wave, because most of us think of this wave when we think of when we have an image of wave in our heads. And so there are a few definitions, a few terms we need to know. The first one is wavelength. Its name kind of gives away what it is. It's the length of one wave. You could measure that length from the beginning of the wave, and it has to be one full cycle, one down and up. So from here to here would be a wavelength, or from here to here. But you could also start in the middle of an up part and go to the middle of the next up part. I'm trying to avoid saying what that up part is called yet because it's the next word. So it's the length of one full cycle. It has a special symbol. It's the Greek letter L, which is a lambda. Lambda. And some people see it as an upside down Y, but those are the very unimaginative people. It's really a dinosaur standing on its back legs with its tail balancing itself, and its head is up here going to eat like leaves off a tree. Okay, so just so you know, it's a lambda. But so it's another letter in the Greek alphabet, and it's simply the length of one full cycle. Okay? The next word that I know you've heard is a crest. A crest is the highest point, reaching for a different color, highest point above. So this line that I've drawn here, this straight line, is called the rest position or the equilibrium position. It's where the medium would be if there was no energy moving through it. So a crest is let me just do it here. A crest is the point of maximum positive displacement. Okay, so it's the highest point on the wave, here or here. Whereas its counterpart is the trough. For those of you that are farm people like I am, you would have heard that word because that's what cattle and stuff eat out of. Okay, so the trough is the lowest point on the wave below the equilibrium or rest position. So the crest is the point of maximum positive displacement, and the trough is the point of maximum negative displacement. Now, if we were looking at a longitudinal wave, instead of crests and troughs, we have points where all of the particles are together, and that's called a compression. and points where the molecules are far apart, and this one you wouldn't have heard of before. It's called a rarefaction. So they kind of parallel the crests and troughs for a transverse wave. Okay? The other thing that I actually drew over here and then stopped myself when I was going to indicate the crest, the height of the wave, or the depth of the wave, okay, is the next characteristic that we need to know. And it is, we used it last unit with springs, it's the amplitude. The amplitude of the wave is how high, how far away it is from the rest position. The distance it is from the equilibrium position. Doesn't matter if it's above or below, so it can be either the positive displacement or the negative displacement. It's a distance, so the direction doesn't matter. So the amplitude is the distance from the equilibrium position to the maximum displacement, whether it's the upper one or the lower one. Now the amplitude tells us about the energy that the wave is carrying. And if you've been lucky enough to be to the ocean, you would know that, right? The more energy a water wave is carrying, the higher the amplitude. Okay, so the greater the energy, the higher the bigger the amplitude. Sound waves, what do you think their how do you think we experience their amplitude? The greater the amplitude of a sound wave, the what? The sound. Letting you think. It's the louder the sound. So if I talk louder, it means I'm putting more energy into the wave, right? And it's gonna, so for sound, the amplitude is its loudness. For light, the amplitude is its brightness. So the bigger the amplitude of the light wave, the brighter or the more intense the light. Now here's the cool thing about amplitude that people always screw up, and that is one cannot speed up a wave by increasing its amplitude. So whether I'm whispering or whether I'm yelling, the speed of my sound wave is going to be the same. The only thing putting more energy in by increasing its amplitude, yelling, the only thing that does is allow other people to hear it more clearly, because it still has a fairly big amplitude when it reaches you. It hasn't lost it all due to friction. Some people think, like, if we were outside playing in the parking lot doing a physics experiment and a car was coming and one person was still standing in the road and I whispered, "Hey, get out of the way." You all might say, "Sister Kay, why didn't you yell so that the wave could have gotten there quicker?" The wave won't get there any quicker. It's just that it will have a louder sound, more energy when it gets there, and it would increase the probability of the person hearing it. If you're sitting on your bathroom floor with your bathtub filled with water and you're creating water waves by putting your finger in and out, the waves are going to travel outward in both directions from your finger. They are going to go exactly the same speed no matter how much energy you hit the surface with. The only thing that hitting the surface with more energy will do is it'll change the height of the wave, but they won't travel any quicker. Okay, so amplitude does not change the speed. All right, the next characteristic of a wave, and there's really two of them that are going to be together. First one is period. And we have a lot of examples of periods of things in our lives. Period is simply the time for one complete cycle. How long it takes for the wave to go through one complete cycle in a medium. We have the period of the Earth going around the sun is 1 year. The period of the Earth rotating on its axis is 1 day. It's the amount of time for one cycle. Because it's a time, its symbol is a T, but we use a capital T because the small t is just time in general. Okay? And so its equation to solve it then would be the total amount of time that has passed divided by the number of cycles that have happened. So if 8 waves go by in 20 seconds, then the period would be 20 seconds divided